Uniform circular motion is one of the basic motions in nature. Uniform circular motion can be described as the motion of a body traveling in a circle with a constant speed. It is a planar motion, where the body regarded as a point mass, travels equal distances along its circular path in equal intervals of time. That is, if the body moves from the point P to the point P' along the path of the arc length s, then the distance s covered by the moving point mass along the arc is given by the speed v times the duration t of the travel, where v is constant. We can also see that the body leaving the point P takes a complete circle and arrives at the point P again. Therefore, uniform circular motion is a periodic motion, that is, the body takes the same time t to complete each revolution around the circle, where t is the period of the motion. Let us consider some examples for uniform circular motion. A typical example is the rotating wheel of a bicycle or other wheeled vehicles. The moving wheel rotates around its axis, and its every point travels along a circular path. If the speed of the rotation is constant, the circular motion of these points is uniform. The next example is the hammer throw, in which athletes gather momentum in a heavy ball at the end of cable, called hammer, that is to be subsequently thrown. Before the hammer is released, some momentum is imparted to the projectile by whirling within a circle. If the thrower spins the ball up to a high speed, in its last revolution goes around a circle with a constant speed, that is, its motion is uniform. A well-known example for such a type of motion is the riding on a Ferris wheel, that is rotating at a constant speed. The passengers sitting on it travel along a circular path and have uniform motion in each ride. An example from nature is the motion of stellar bodies in spiral galaxies. The stars regarded as point masses with respect to radii of such galaxies, orbit the center of the spiral galaxy and maintain a uniform circular motion for millions of years. Uniform circular motion is an accelerating motion. Although the length of the velocity vector is constant, its instantaneous direction is different in each point along the circular path. That is, the magnitudes of the velocities in the point P and P' are equal, but the directions of the vectors v and v' are different. Therefore, the acceleration of a body maintaining uniform circular motion does not vanish. Now we determine this acceleration. We will compute both the direction and the magnitude of the acceleration of a point mass traveling on a circle with a radius or around the center O. We start to measure the time t when the body passes through the point P. The velocity vector v of the point mass in the point P is the tangent to the circular path in that point. During the time interval between 0 and delta t, the point mass travels to the point P', where it has the velocity v'. Let us denote the velocity of the body at the points P and P' with the vectors PA and P'B, respectively. The arc length between these points covered by the moving point mass during the time delta t is denoted by delta s. If delta phi is the central angle corresponding the points P and P' on the circle, then the delta s is equal to the radius r times the angle delta phi. Now we translate the vector v' into the point P and denote it with the vector pc. The difference delta v between the vectors v and v' is given by the vector ac. Since the vector pa is perpendicular to the vector op, and the vector pc is perpendicular to the vector op', the angle apc is equal to the angle pop, which is delta phi. We also see that the triangle apc is an isosceles triangle, and the angle PAC is equal to 90 degrees minus delta phi divided by 2. If we consider an infinitesimal time interval for the motion, that is, if delta t tends to 0, the point P' approaches the point P. As a result, delta phi also tends to 0, and the angle PAC approaches the right angle, and the difference vector delta v becomes perpendicular to the vector v. Since the acceleration is defined by the derivative of the velocity with respect to the time t, which is the ratio of delta v to delta t with delta t approaching 0, the acceleration of the point mass traveling on the circle is perpendicular to its velocity. Because of its direction, the acceleration of a body moving along a circle at a constant speed is called centripetal acceleration. The magnitude of the difference vector is equal to pa times delta phi, which is the magnitude of v, times the angle delta phi. If we substitute the equation obtained for the arc length delta s into this expression, we obtain v times delta s over r. Since the magnitude of the acceleration is just the derivative of the magnitude of v with respect to the time t, it can be written as v over r, times the derivative of the arc length with respect to the time t. The derivative is just the speed v, and we obtain v squared over r. Now, we have determined both the direction and the magnitude of the centripetal acceleration. These findings can be summarized in the following statement on centripetal acceleration. The acceleration of a body moving on a circle with a radius r, at a constant speed v, points toward the center of the circle, and its magnitude is given by the square of the speed v divided by the radius r. Uniform circular motion can be described by the vector r rotating around the center O of the circle, while it always points to the instantaneous position p of the body moving on the circle. We denote the position vector r with the letters OP, where we chose the center O of the circle as the reference point of the motion. If we attach a polar coordinate system to the origin, we can measure the arc length along the circle with the azimuthal angle phi, that is, the arc length s is equal to the radius r times the angle phi. We can also express the angle phi as the ratio of the arc length s to the radius r. We define the angular velocity omega of the body traveling on the circle as the derivative of the central angle phi with respect to the time t. This quantity describes the angular rate of the rotation of the position vector pointing to the object moving on the circle. The unit of the angular velocity is inverse of time. If we use SI, it is measured in reciprocal second. Since we discuss uniform circular motion here, the angular velocity is constant during the revolution of body along the circle. As a result, angular velocity is simply the ratio of the central angle phi to the time t, during which the position vector r of the moving body rotated through the angle phi. That is, the rotation angle phi is directly proportional to the time, and the proportionality factor is the angular frequency omega. Since the arc length s covered by the moving point mass is equal to the radius r times the central angle phi, for uniform motion we can eliminate the angle from this equation, and we obtain r times omega times t. We have seen that the velocity vector v of the point mass is the tangent to the circle in the point P. Its magnitude, the speed v, is just equal to the arc length s divided by the time t, and we can express the speed v as the product of the radius r and the angular frequency omega. As already stated, uniform circular motion is a periodic motion with the period t. Then we can express the angular velocity omega as 2 pi over the period t. We can also introduce the frequency nu of the rotation, which is the reciprocal of the period t. It can be written as the angular frequency omega divided by 2 pi, and it has the same unit as of angular frequency. Finally, we express the centripetal acceleration in the term of the angular frequency as well. We saw that the magnitude of the acceleration is given by v squared over r. Since omega can be written as v divided by r, the acceleration is equal to the speed v times the angular frequency omega. But v is equal to r times omega, and we obtain omega squared times r. We described circular motion in the polar coordinate system with the center of the circle as the origin of the coordinates. Since the polar coordinates are adapted to the symmetry of the motion, this description provides a straightforward derivation of the equations of motion for a body traveling on a circle. The radial coordinate r is simply the length of the rotating position vector pointing from the center O to the instantaneous position p of the body. The azimuthal angle phi is the central angle measured between the position vector and the x-axis. We already presented the kinematic quantities of any moving point mass in polar coordinates. The components of the position vector of the point mass are the radial coordinate r and the azimuthal angle phi. Both are functions of time. We found that the radial component of the velocity of the point mass is simply r dot, and its angular component is given by r times phi dot. We also derived the components of the acceleration in polar coordinate system. Its radial component is equal to r double dot, minus r times the square of phi dot. Its angular component is given by r times phi double dot, plus 2 times r dot times phi dot. From the kinematic quantities written in polar coordinates we obtain the equations of motion for circular motion, if we apply the condition stating that the length of the position vector is equal to the radius of the circular path, which is constant. As a result, the derivative of the radial coordinate of the position vector with respect to the time vanishes. With this condition, the kinematic quantities reduce to the following set of expressions. For the components of the position or displacement vector of the body we have a constant radial coordinate, which is equal to the radius of its circular path, while its angular coordinate still depends on time. The radial component of the velocity of the body traveling around the circle vanishes, and its azimuthal component remains r times phi dot. Both the components of the acceleration of the body reduce to the following expressions: its radial component is equal to minus r times the square of phi dot, and its angular component is r times phi double dot. These component equations demonstrate that the velocity v of the body is perpendicular to its position vector r. For uniform circular motion, we have an additional condition stating that the position vector rotates with a constant velocity around the circle. Therefore, the angular velocity omega, that is the derivative of the azimuthal angle with respect to the time, is constant. As a result, the second-order derivative of the azimuthal angle of the position vector vanishes. If we apply this condition, we can derive the equations of motions for uniform circular motion. The position of the body is given by the radial coordinate r, which equal to the radius of the circle, and the azimuthal angle phi, which is equal to the angular velocity omega times the time t. The velocity of the body is the following. Its radial component vanishes, while its angular component is equal to the angular velocity omega times the radius r. The acceleration of the body has the following components. Its radial component is given by minus the square of the angular frequency omega times the radius vector r, while its angular component vanishes. These equations demonstrate that the acceleration of the moving body is perpendicular to its velocity. We also see that the position vector and the acceleration are antiparallel, that is, the acceleration points in the opposite direction to the position vector. Therefore, the acceleration always points into the center of the motion, and we can talk about centripetal acceleration. Non-uniform circular motion is a more general form of motion, where the speed of the body is not constant along the circle. Here we can also use the examples mentioned earlier in the case of uniform circular motion. When we speed up a bicycle, its wheels rotate faster and faster. This is also true in the case of hammer throw, where hammer speed follows a generally increasing trend during the throw. Ferris wheels stop when passengers are boarding. Then they start to rotate again and are brought up to their constant operational speed. Since the speed of the body depends on time, its position can be described with the constant radius r of the circular path and the central angle phi, which is an arbitrary function of the time t. Then the angular velocity omega, which is the derivative of central angle phi with respect to the time, may also depend on time in the general case. If we define the angular acceleration alpha as the derivative of the angular velocity with respect to the time, then the angular acceleration is the second-order derivative of the central angle phi with respect to the time. In the general case, we can say that alpha depends on time as well. If alpha is constant, we talk about uniformly accelerating circular motion. In the case on non-uniform circular motion, both the direction and the magnitude of the velocity are changing along the circular path. Therefore, the speed of the traveling point mass will not be necessarily the same in the points P and P'. Let us denote the speed of the body in the points P and P' with v and v' again, where v' is equal to v plus delta v. The velocity v is represented with the vector pa, and the velocity v' is represented with the vector p'd, which is the sum of the vectors p'b and bd. By using this vector sum, we can decompose the rate of change of velocity into two parts. First, we translate the vector p'b into the point p, which is equal to the vector pc. Then we construct the difference vector ac of the vectors p'b and pa, and compute the rate of change of this difference, that is the length of p'b minus pa divided by delta t. Here the interval delta t is the elapsed time of travel between the points p and p'. If delta t tends to 0, this rate approaches the ratio of the square of speed v to the radius r, that is the value of the centripetal acceleration, as in the case of the uniform circular motion. The other rate of change of the velocity is measured in the tangential direction, and is given by the length of vector bd divided by delta t. The length of the vector bd is just the magnitude of delta v. This rate approaches the time derivative of the speed v, if delta t tends to 0, which is the tangential acceleration of the body moving on the circle. As a result, we can state the following. In the case of non-uniform circular motion, the acceleration can be decomposed in radial and tangential directions. The radial acceleration of the body is the centripetal acceleration, which is given by the square of the instantaneous speed v divided by the radius r, times the negative of the position vector r divided by its length. Here the negative of the normalized position vector gives the normal vector pointing from the position of the body toward the center of the circle. The tangential acceleration of the body is equal to the derivative of the speed v with respect to the time t times the normalized velocity vector v, which gives the unit tangent to the circle in the given point. The net acceleration of the body traveling on the circle at a non-uniform speed is the sum of the radial and tangential accelerations at any point of the circle. We have already described the motion in polar coordinates to derive the equations of motion for uniform circular motion. We use the same method to obtain the equations of motion for non-uniform circular motion as well. We apply the same polar coordinate system with the center of the circle as the origin of the coordinates. The radial coordinate r is the length of the rotating position vector pointing from the center O to the instantaneous position p of the body. The azimuthal angle phi is the central angle measured between the position vector and the x-axis. The general expressions for the kinematic quantities of any moving point mass in polar coordinates are the same as before. The components of the position vector of the point mass are the radial coordinate r and the azimuthal angle phi, and both are functions of time. The radial component of the velocity of the point mass is equal to r dot, and its angular component is given by r times phi dot. The radial component of the acceleration is equal to r double dot, minus r times the square of phi dot. Its angular component is given by r times phi double dot, plus 2 times r dot times phi dot. For circular motion, we have applied the condition stating that the length of the position vector is equal to the radius of the circular path, which is constant. Then the derivative of the radial coordinate of the position vector with respect to the time vanishes. As a result, we have obtained the following set of expressions. For the components of the position or displacement vector of the body, we have a constant radial coordinate, which is equal to the radius of its circular path, while its angular coordinate still depends on time. The radial component of the velocity of the body traveling around the circle vanishes, and its azimuthal component remains r times phi dot. Both the components of the acceleration of the body reduce to the following expressions. Its radial component is equal to minus r times the square of phi dot, and its angular component is r times phi double dot. Since the derivative of the angular coordinate phi with respect to the time t is equal to the angular velocity omega, we can summarize the equations of motion in the following forms. The position of the body is given by the radial coordinate r, which is equal to the radius of the circle, and the azimuthal angle phi, which is an arbitrary function of the time t. The velocity of the body is the following. Its radial component vanishes, while its angular component is equal to the angular velocity omega times the radius r, and it is equal to the speed v of the body measured along the circle. The acceleration of the body has the following components. Its radial component is given by minus the square of the angular frequency omega times the radius r, while its angular component is equal to the radius r times the derivative of the angular frequency omega. Since the radial coordinate r of the moving body is constant, this expression is just the derivative of the speed v with respect to the time t, as we expected. These component equations demonstrate that the velocity v of the body is the tangent to the circular path in the point P, that is, the velocity of the body is perpendicular to its position vector r. However, the acceleration can be decomposed into two components now, the centripetal acceleration pointing towards the center of the motion, and the tangential acceleration pointing into the direction of the tangent to the circle. The centripetal acceleration is equal to minus the square of the angular velocity times the position vector r. The tangential acceleration is simply the derivative of the speed v with respect to the time times the normalized velocity, which is the unit tangent vector to the circle in the point P. Since the acceleration is the vector sum of the centripetal and the tangential accelerations, it is no longer perpendicular to the velocity, and it is not parallel with the position vector.